Swayam Prabha. Digital India. Educated India.
Okay, so in this lecture we'll talk about diffusion between phases. So in a single phase, if there is a concentration gradient or chemical potential gradient, diffusion will set in. In the case of two immiscible phases in contact, mass transfer or diffusion will set in when there is a difference in the chemical potential of the two species. Okay, so in two immiscible phases in contact, diffusion or mass transfer sets in when there is a difference in the chemical potential of a species, let's say A. Okay, so this mass flow between the two phases will continue until the chemical potentials are equal. So generally our interest here is, if you start a system which is away from equilibrium, you wanted to study what is the rate of mass transfer with respect to the driving force. In this case, the driving force is the chemical potential difference. Okay, so we would like to study how to express mass transfer rate proportional to the driving force. So driving force here could be mu A at some phase, let's say gas phase, minus mu A in another phase, liquid phase. Okay, so mass transfer will happen as long as there is a finite difference. When this chemical potential can become equals to 0, the chemical potential difference becomes equal to 0, then the mass transfer will also stops. So that's what we call as a equilibrium system, which we saw in the last class as well. Now we will discuss this in a little bit detail by considering an example. Okay, so to go further, we would like to think about a simple gas liquid contact system to illustrate some of the concepts of interface mass transfer. Okay, so we're going to discuss something called a wetted wall column. Wetted wall column. This is the simplest or a simple gas liquid contacting system. So this is basically a kind of a pipe, a hollow tube, and a gas flows in here. Okay, gas flows upward. So this may have, for example, air plus ammonia in our example. Okay, it goes upwards, flows upward, and then leaves at the top. So ammonia would be high in concentration at the bottom, and it will be lean here. Okay, so this is gas out. This also contains air plus some amount of ammonia, but the concentration of ammonia here at the outlet will be less compared to the inlet. This is because we are actually having a liquid reservoir. This is a liquid reservoir. And through this particular mechanism, the water basically flows into the pipe, not as a bulk, but as a thin film surrounding the inner walls of the tube. Okay, so it trickles along the inner wall of the pipe. Okay, so then so this liquid actually flows downward because of gravity. Okay, the thickness of this film here can be controlled by the opening here. So by this particular very simple apparatus, the liquid is flowing from top to bottom and the gas is flowing from bottom to up. So this is a counter current flow of two phases, counter current flow. So liquid flows down, gas flows up. So you can think about a steady state operation where the flow rates are steady. Okay, and because of this contact between the gas and the liquid near this interface, this is an interface, the wavy curve, the wavy line that I have drawn here is basically the interface between the liquid and the gas. At that particular location, the mass transfer will happen because they are in direct contact. Ammonia will try to diffuse from the gas phase to a liquid phase. Okay, and then it's flowing down, and then the liquid can be collected here and the gas can be collected at the top. So this is a very simple apparatus called weighted wall column. So now what we would like to do, we'll take a small section here and then look at how concentration varies when you go from a gas phase to a liquid phase. Okay, from the bulk of the gas to bulk of liquid. So here we are going to write concentration of ammonia, which is a solute, or I call it as just A. The symbol A here refers to the solute ammonia. The x-axis here is the distance. So you're actually looking from here and then you're moving towards from the bulk of the gas to the bulk of the liquid, crossing the gas liquid interface. So when you are here at this point, you are actually in the bulk of the gas. So maybe you start somewhere here. Okay, this is something we call it as YAG. So YAG is the mole fraction of A in the bulk gas. It's supposed to be an average quantity, okay, because it represents the bulk concentration of A in gas. So you start here and then you move further down. So you'll see this remains constant because you're still in the bulk, and then you're going to reach the interface. So let's say the interface is marked here as a vertical line, and then when you come closer to the interface, what will happen is the concentration actually drops here, and this we will call it as YAI. YAI is the mole fraction of A at the interface. So here the interface is given as a one thin line, the dotted line here. In reality, the interface will have a finite thickness of few molecular layers, but for this particular purpose, we will imagine the interface to be a line here. Okay, so this is the interface. You are looking at very locally. So this is YAI. Now if you cross further, you are going into the liquid phase now. Okay, so the liquid phase concentration will not start here, it will start a little bit above or maybe below, and then it will have a signature like this. Okay, so this is your XAL. XAL is the mole fraction of A in the bulk liquid, whereas XAI is the mole fraction of A at the interface. So you can see there is a discontinuity in the concentration of the species at the interface. The interface is the same place, but if you look at the concentration of the gas in the interface, it has YAI, whereas in the same location, the concentration of the same species in the liquid phase is actually XAI. So that means at the interface, the two concentrations are not equal. Okay, there is a jump, there is a discontinuity. Okay, so that is a characteristic of an interface. Now in this case, YAG and XAL, these are the bulk concentrations corresponding to this particular location of the column. Okay, I'm talking about a particular location in the column. The column is operating at a steady state condition. In this particular location, the bulk value of the mole fraction in the gas phase is YAG, and in the bulk liquid somewhere here is XAL. Okay, now these are not at equilibrium. Okay, the YAG and XAL is not at equilibrium, they are actually away from equilibrium. Now the question we would like to ask is, how can I write an expression for mass transfer rates when you are away from the equilibrium values? Okay, so that is the context, that is the question we would like to write. So we may be tempted to write something like mass transfer flux, let's say NA, is something proportional to YAG minus XAL. Okay, we may be tempted to write something like this, but this is incorrect, because this particular law says that the mass transfer flux will become 0 when YAG becomes equal to XAL, as if at equilibrium the concentration of the species in gas phase and liquid phase should be equal, but that is not the case. We already said the concentrations of the species are not equal, but only the chemical potentials are equal. So what we would like to write is actually Na proportional to mu A at gas phase minus mu A at liquid phase. This is how we should be writing, because by this law we can show that the mass transfer flux will become 0 the moment mu Ag and mu L are equal. Okay, so that's consistent with thermodynamics, right? But the problem with this expression is that unlike the mole fraction, which is a measurable quantity in experiment, the chemical potentials are not measurable in experiment directly. Unlike a thermometer or barometer, there is no chemical potential meter that you can use to measure chemical potential of the species. It is indirectly calculated by some other means. Okay, so from a practical point of view, we are faced with this particular challenge that the right expression is to use chemical potential, but it's not measurable readily. Mole fractions are readily measurable, but we can't write them as a simple difference in the mole fractions. So that's a dilemma, so that's a challenge. Okay, so we want to resolve this particular issue. So the way forward this would be thinking about going back to this particular expression. We could think about the mass transfer to be controlled by three things. The two bulk phases. Okay, there is a mass transfer resistance in the gas phase and there is a mass transfer resistance in the liquid phase. That's the reason why there is a gradient in the concentration on both phases. Okay, and then there could be some resistance in the interface also. Okay, for simplification, what we are going to do is we are going to say this interfacial concentration XAI and YAI are at equilibrium. That's an assumption we are going to make. Okay, so therefore when we say the interfacial concentration XAI and YAI, we will say that that is related to equilibrium concentrations. The logic behind this is to think about this interface to be a very thin volume or thin area, or thin region in which the gas and liquid are always at equilibrium. Therefore, the interfacial concentration YAI and XAI are always at the equilibrium line. Okay, so we are going to make an assumption that interface has no resistance to mass transfer. The implication of this assumption is that we are able to say YAI is actually Y star, XAI is actually X star, where these two are obtained from an equilibrium relations, something like this. Okay, so this is the equilibrium curve which I talked about in the last class. So the concentration at the interface is governed by equilibrium curve, equilibrium law. Therefore, the mass transfer rate that we want to write can be now described within the bulk phases, okay, and associated resistance. Okay, we are going to say the resistance for mass transfer happens to be in the gas phase here as well as in the liquid phase here, the total mass transfer. Okay, and mass transfer resistance lies in the bulk phases of gas and liquid. And this is something we call it as two resistance theory. Now let us plot this particular information in a slightly different way so that we can relate this to a equilibrium curve. Okay, so I already showed the equilibrium line y versus x. So imagine this is your equilibrium line. So this is the equilibrium curve. So let's say the point here I was trying to make, at any given location here, the bulk concentration was given by YAG and XAL. This particular combination of YAG and XAL can be represented here as a point. Okay, this point P can be represented as a combination of YAG and this is XAL. Remember, what I'm trying to do here is I'm trying to plot two different things. In here, I showed how concentration varies when you go from bulk gas to bulk liquid across the interface at a given location of the instrument. Okay, that is this information. Now what I'm going to do is, in the same location, I am plotting the concentration of the bulk phases YAG and XAL along with the equilibrium curve, just to show the departure from equilibrium. Okay, so when you make these two phases in contact, you want this concentration to be in this equilibrium line, but you are starting at some point here. There is so this point P is actually lies away from the equilibrium line. So that is the driving force for the mass transfer to happen. You are actually away from the equilibrium curve. Now the mass transfer will happen so that this point will move closer to the equilibrium line. Okay, it kind of illustrates where this non-equilibrium lies. Now what happens is let us also point that the interfacial concentration, which I said is equal to equilibrium concentration, is somewhere here. This is YAI and this is XAI, and we call this as point M. So whatever concentration profile I showed here, I am replotting this along with the equilibrium line. This point P here suggests the composition of the bulk phases XAG and XAL, whereas the interfacial concentration lies on the equilibrium line, because I am assuming that the interface has no additional mass transfer effect. So the interfacial concentrations are equal to the equilibrium concentrations. So XAI and YAI should be lying on the equilibrium line. I am denoting that as M, right? So now I already said this instrument is actually operating at steady state conditions. So we can write that whatever mass that is leaving from the gas phase should enter into the liquid phase, and the interface has no accumulation term. Okay, so we can write the rate of mass transfer from YAG to YAI, because this is the mass transfer happening in the gas phase with the concentration difference from YAG to YAI, and this should be equal to rate of mass transfer from XAI to XAL. So in this particular case, we are assuming steady state. This is a steady state assumption. And here we assume that the solute is transferring from gas phase to liquid phase. You can also write the same equations if you have the opposite stripping operation or desorption operation, where the solute comes from liquid phase to gas phase. So now if you want to write this mass transfer, we can use this NA is equal to KY into YAI, YAG minus YAI. This should be equal to KX XAI minus XAL. So this Kx here is the local mass transfer coefficient in the liquid side. This Ky here is the local mass transfer coefficient in the gas phase. So at steady state, whatever mass that is getting transported from the bulk of the gas to the interface must be swept away by the other side, which is the liquid side, from the interface to the bulk of the liquid. So that's what this equation means. This XAI and YAI lies in this particular interface. Okay, so we could rearrange this equation as YAG minus YAI by XAL minus XAI is equal to minus Kx by Ky. We are able to write this because this Na here is the same whether you use from the mass transfer of the gas side or the liquid side. Okay, so by equating these two, you can show this particular relationship. What this means, what this tells you is that this particular equation is an equation of a line that connects the point P and M with a slope of minus Kx by Ky. Okay, so if you know Kx and Ky, which is a mass transfer coefficient, then the concentration, the mass transfer is given by this particular driving force line. The line that is connecting P and M, we are going to call it as, this is called a driving force line. We already talked about equilibrium line. Now I am introducing another terminology called driving force line, which tells you that if you are away from the equilibrium, when you are a non-equilibrium state and you are trying to approach the equilibrium, the path with which this concentration will reach the equilibrium value is given by this driving force line. So this particular equation is very important because if I know Kx and Ky and YAG and XAL, these are all measurable quantities, and there is also relationship between YAI and XAI, through the equilibrium line, then we can get what is the equilibrium concentration or the interfacial concentrations. Okay, so we know that YAI as a function of XAI because of the equilibrium line XAL and YAG, these are all actually measurable quantities experimentally. These are measurable values. Kx and Ky can be known. Okay, this can be something measured from control experiments. Okay, with all these things, then we have only one unknown and we can solve for that. Once you know what is the importance of knowing the interfacial concentration is that once you know the XAI and YAI, I can go back here and I can calculate the mass transfer rate. Ultimately, this is what I was hoping for. If I know where I am from the equilibrium line, away from the equilibrium line, and I want to calculate what is the mass transfer rate, and the mass transfer rate is given by these expressions. To calculate this Na, I need the mass transfer coefficients as well as the interfacial concentrations. Okay, so now let us take an example and show you how to calculate the interfacial concentrations at the same time the mass flux also. Let's say this Kx value is given as 3 into 10 power minus 3 in the units of kilomole per meter square second mole fraction, and Ky is 1.5 into 10 power minus 3 kilomole per meter square per second per mole fraction. And the equilibrium line is given as 3 times AXI. Okay, this is equilibrium line. So two mass transfer coefficients are known and equilibrium line is known, and you may be asked to calculate what are the interfacial concentrations, what are the interfacial or mole fractions, and the mass transfer rate Na. Okay, so first we know this equation here, the equation of the driving force, and the slope of that line is minus Kx by Ky. So this is basically minus 2 here, and then you can go to this equation YAG minus YAI divided by XAL minus XAI. This is equal to minus 2. Now I can substitute for YAI using the equilibrium line. So I'll get YAG minus 3 times XAI to minus 2. Okay, so what is also given, which I forgot to mention, is you also know the measurable YAG and XAL. Okay, these are also known. This is 0.8, this is 0.05. So you can rearrange this. You'll get this as 0.18. Once you know XAI, you can solve for YAI from equilibrium line, which is 3 times XAI So this is 0.54. Yeah, that is true. Yeah, this is true. This is true. Yes. Yeah, you'll get plus symbol here. And so basically you have got xai, which is 0.18, and then yai, which is 0.54. So the interfacial concentrations are known. Kx, ky also known. Okay, so now you can calculate Na in two ways. Either you can use the gas phase mole fractions, or you could also use the liquid phase compositions. So what we are able to do in this example is that if I know the initial concentration of the two contacting phases, and if I know the mass transfer coefficients, then I'm able to actually calculate the mass transfer rate. So going back to this weighted wall column, if the problem statement I given as somewhere here corresponding to xal and yag at this particular point, the mass transfer rate at that particular point would be this. Okay, if I take a different point somewhere here, I might have another point, operating point, a point somewhere here. Okay, and then a mass transfer will happen along this particular driving force line. Okay, and if you go a little further up, you may go to another line here, or from P, if you go down, you'll probably go to some other points like this. So these are all different points along the equipment corresponding to bulk concentrations. At each of those locations, you can calculate what is the interfacial concentration, then you know what is the driving force, then you can calculate what is the mass transfer rate, right? So even though this particular approach says that you can actually use interfacial concentrations to calculate mass transfer, we generally try to avoid the use of interfacial concentrations and try to use something more practical, okay, or more readily available information. Okay, so this basically brings us to the definition of what is called the overall mass transfer coefficients. What I have used in this example is the local mass transfer coefficient pertaining to the individual phases. Okay, now it may be also possible to write the overall driving force not using the interfacial concentration, but using only the bulk concentration and the equilibrium concentrations, and then thereby define a modified version of the mass transfer coefficient. Okay, this basically takes us to the definition of overall mass transfer coefficient. So to illustrate this idea, let us again go back to the same plot. I am plotting y versus x mole fractions. This is my equilibrium line. So my point P is here. This is YAG and the corresponding XAL. This denote a bulk concentration of the two phases. Okay, and the point M is here denoted by YAI, the interfacial concentration we talked about just now. Okay, so now in our analysis just now we used this particular driving force YAG minus YAI to calculate the mass transfer, or we used this particular driving force which is XAL minus XAI, right? The two driving forces we have used. Now instead of using this particular interfacial concentration, we may be able to use a different kind of driving force, and that is, let us say that we want to write the total mass transfer rate corresponding to the driving force YAG minus, which we call this is Y star, okay, YA star. What is YA star? YA star is the concentration, equilibrium concentration with XAL. So XAL is the bulk concentration of the liquid. Corresponding to that, there would be an equilibrium concentration in the gas phase. That would be actually YI. So the way I am finding YA star is the equilibrium value corresponding to XAL. XAL is the bulk liquid concentration. Corresponding to that, there will be an equilibrium gas phase concentration, which is what YA star. So what I am hoping to do is, instead of using this particular concentration difference, how about using YAG minus YA star? Okay, why I am saying this? Because YA star is easy to find. Because I know XAL, I know the equilibrium line, right? So I can calculate YA star easily. I don't have to go about calculating this interfacial concentrations separately. Okay, so let me rephrase again. What I'm hoping to do is try to write the mass transfer driving force as YAG minus YA star, where YA star is the equilibrium concentration corresponding to XAL. Since XAL is known and equilibrium line is known, I can substitute XAL in the equilibrium line and get YA star, and then use an effective driving force as YA star minus YAG minus YA star instead of the actual YAG minus YAI. So YAG minus YA is the actual driving force, and I've shown how to use that. Okay, but if I want to avoid the interfacial concentration and rather use something more readily calculatable, I would like to use YAG minus YA star. This is also true for the liquid phase. We would write this as the driving force. Generally, XAI minus XA star, XAL was the driving force when we use the local coefficient. Instead, we could think about finding a equilibrium concentration corresponding to YAG. Then I would be able to use this particular concentration difference. So that is XA star minus XAL instead of XAI minus XAL. So I would have used XAI minus XAL with Kx, but instead I could use this particular concentration difference, and I can also easily get XA star here because I know YAG. Corresponding to YAG, there will be an equilibrium concentration at the liquid phase, which is XA star. So by making use of either this point or this point, I can readily express the total concentration gradients without recourse to the interfacial concentrations. So that's the idea. But if I do this, I'm not using the right driving force, isn't it? I'm over specifying my driving force. The actual driving force is only this, but I'm hoping to use this. So my driving force is different. So my mass transfer rate will also be different. The way to correct that would be to change the mass transfer coefficient so that it can offset the change in the driving force. So my flux has to be the same, whether I use the interfacial concentration or the total equilibrium concentration difference. The total flux has to be the same. So when I change the driving force, I have to change my mass transfer coefficient also. And this can be done both in gas phase as well as in the liquid phase. So first I will do it in gas phase, and equivalently one can do in the liquid phase also. So we would like to write this Na as some overall mass transfer coefficient capital Ky times YAG minus YA star, where YA star, as I said, is the one that is in equilibrium with XAL. XAL is the bulk liquid concentration. Instead of writing Na as small kx, small ky, this should be small ky YAG minus YA. It is just a different ways of writing the mass flux here, mass transfer rate. Here I am using a different driving force and a overall mass transfer coefficient. Here I am using the correct actual driving force for mass transfer, and I am using the local mass transfer coefficient. They are differentiated by small ky and capital Ky. Okay, so this is supposed to be capital Ky. So this is I call as overall mass transfer coefficient. I'm going to call MTC, and this is a local MTC, mass transfer coefficient. Okay, they both have the same units, but the driving force are different in the two cases, so that NA will be same either ways. Okay, so now if you look at this particular graph, okay, you can see this YAG minus YA star can be written as this difference plus this difference, that is YAG minus YAI plus YAI minus YA star, isn't it? I am writing the total driving force as sum of two driving forces. One is YAG to YAI and another one from YAI to YA star. Right? Now what we are going to do is this particular line connecting YA star and YAG, I am going to draw a line here connecting these 2 points, and let's say this particular line has a slope m prime. Okay, so that I can write that YAI minus YA star is equal to m prime times XAI minus XAL. Okay, so here I am introducing a new a slope of the line connecting the two superficial concentration here and then the concentration here. And the reason for doing that will be very clear now, that we will write this as YAG minus YAI plus m prime times XAI minus XAL. So this is the total driving force. Now from this equation we can write this is nothing but NA divided by KY. What is this? How can we write it in terms of NA? This is also NA divided by small ky, yes, plus m prime. What about this? Remember this equation? So this will be m prime divided by small kx times NA here. So now NA is common for all, so we can cancel this. So you will get 1 by ky is equal to 1 by small ky plus m prime by kx. So this is the definition of overall MTC ky. So going back here, if I want to write the mass transfer rate as the concentration difference YAG minus YA star, this entire concentration difference, then I have to use a mass transfer coefficient KY, overall mass transfer coefficient KY, which is basically function of the two local coefficients. Okay, I think we're running out of time, so we'll stop here and then I'll continue in the next class about with an example of these calculations.